Hello, this question is taken from GATE 2008 exam. It's a 2 marks question where we need to compare a non-pipelined version of a CPU with the pipelined one. The pipelined one has 5 stages with these delays, and then we need to calculate the speed up. First, let's just read the statement. A non-pipelined single cycle processor operating at 100 MHz is converted into a synchronous pipelined processor with 5 stages requiring 2.5, 1.5, 2, 1.5 and 2.5 nanoseconds respectively. The delay of latches is 0.5 nanoseconds. The speedup of pipeline processor for a large number of instructions is. Just have a look at these options and now we'll solve the question. So they are saying this processor runs at 100 megahertz. 100 megahertz means 100 into 10 raised to the power 6 hertz, okay, which means 10 raised to the power 8 clocks in 1 second, okay, because hertz obviously means number of times per second. So this is 10 raised to the power 8 clocks in 1 second. Now just to simplify things, we know that other units are nanoseconds. So let's try to convert this also into nanoseconds. You just write 10 raised to the power 8 into 10 clocks. 1 into 10 seconds. Okay. I generally just tend to convert everything in nanoseconds. This way it makes the question a lot easier to solve. Okay. We have just multiplied both sides with 10. Now it comes out to be 10 raised to the power 9 clocks in 10 seconds. Okay. Which obviously means 1 clock takes 10 nanoseconds. You just take this 10 raised to the power 9 to this side. It will get divided by 10. That means 1 clock takes 10 by 10 raised to the power 9 seconds, which is equivalent to saying as 10 nanoseconds. And now let's analyze this pipelined version. In pipelined version, you can see the maximum stage delay is 2.5 nanoseconds. So we are going to consider this one as a stage delay for all of the stages because we want a constant clocking rate. We have studied this in theory lectures that the stage with the maximum delay is considered. Okay, because if you give 2.5 nanoseconds to each of the stage, they'll obviously finish their work because they either require 2.5 or less than 2.5. Okay, so stage delay is 2.5 plus 0.5 nanoseconds for latches. We have already seen that diagram, no? Between every stage, we have placed some buffer. These buffers or latches require 0.5 nanoseconds. Stages require 2.5 nanoseconds. In total, this comes out to be 3 nanoseconds. Okay, 2.5 plus 0.5, 3 nanoseconds. Now you just know the formula for speed up. It's time taken by non-pipelined processor divided by time taken by pipelined processor. That means it is 10 nanoseconds divided by 3 nanoseconds. Speed up. This is your answer, 3.33. Now, one thing that I haven't yet considered is this processor it takes 10 nanoseconds to generate one clock signal. How I am considering that 10 nanoseconds are taken for one entire instruction? How can I say that? 10 nanoseconds are for one clock, but I am considering that 10 nanoseconds are taken by one instruction. I am saying so because the first line of question is a non-pipelined single cycle processor. Single cycle means each instruction takes only one cycle, one clock cycle. So I can very easily say that one instruction takes one clock cycle, which in turn means 10 nanoseconds. That's why I've written 10 nanoseconds. Next thing that needs to be explained is, here we have assumed that stage delay is 2.5 and plus 0.5 for the latch delay or buffer delay. That means here clock rate is 3 nanoseconds. So how can I assume each instruction here takes 3 nanoseconds? This one 3 nanosecond what we just calculated is clock rate or the time period for clock. How can I say one instruction takes this much time? It's because of the line. For a very large number of instructions, we have very large number of instructions. That's why we can easily consider 3 nanosecond to be the amount of time required for one instructions. Because for very large instructions, we can assume the CPI to be 1. Clocks per instruction is 1. And one clock here takes 3 nanoseconds. Now, how is this possible? Because for very large number of instructions, only one instruction is the exception. The first one. First instruction requires all 5 stages because at the time pipeline is empty. 5 stages into 3 nanoseconds for each of the stage. That means 15 nanoseconds. First instruction requires 15 nanoseconds. But every other instruction, that means second, third, fourth, so on till a very large number, each of them is going to take 3 nanoseconds only. Okay. So the remaining n-1 instructions will take 3 nanoseconds. Now what happens? As this number grows, we consider n to be a very large number. We can simply neglect this 15. Initial first instruction can be neglected because that's the only one exception. Okay. So you can say overall it is 3n instructions. Sorry, not 3n instructions. This is the time required in nanoseconds, 3n nanoseconds, where n is the total number of instructions. Now calculate the time required for one instructions. You just divide it by n, and you are left with 3 nanoseconds. So for very large number of instructions, you can simply say CPI is equal to 1 and one clock takes 3 nanoseconds. That means one instruction also takes 3 nanoseconds. Okay. So that's how I got this. Your answer is 3.33.